Welcome back to our course on memory device technology for AI/ML computing. I'm your instructor, Dr. Shubhadeep. So let us try to recall what we studied the last time around. In the last class, we had a thorough introduction for resistive random access memories, or RRAMs. In this section, we saw how RRAMs, which are nothing but a vertically integrated metal insulator metal structure with a functional element called the filament, is basically used as a memory element which can switch back and forth from high resistance state to low resistance state by successive creation and annihilations of this element called the filament. We also saw that RRAMs, due to their superior scalability, speed, and endurance, but more importantly by the fact that the process and materials involved in RRAMs are very much CMOS compatible, they are one of the most promising candidates in the eNVM space. All these factors translate to better integration with existing manufacturing infrastructure, therefore lower manufacturing costs and better cost per bit. Finally, we also saw that depending on the nature and creation or dissolution process of these filaments, several varieties of RRAMs are present, but we divided them into two main subclasses called the valence changer RAM or VCRAM and the conductive bridge RAM or the CBRAM. So let us today begin with the valence changer RAM or the VCRAM. Remember, here the top and bottom electrodes constituted of the noble materials, high work function metals like gold, platinum, palladium, and the functional filament was formed because there was a valency change in the metal oxide, and this localized substoichiometric oxide is what creates the conductive filament. Okay, so the first question that we will try to ask today is, what is the physical mechanism by which this filament is formed? Now remember, what we are going to do is, you have this metal insulator metal structure, and in the prototypical system this constitutes of a metal oxide. So in a metal oxide, the metal is the cation and the oxygen is the anion. So what happens is, for the creation of these conductive filaments, you start cranking up the voltage on the top electrode while you keep the bottom electrode grounded. So as you can see in this particular graph, we are applying a voltage on the top electrode and measuring what is happening to the current also from the top electrode. So because this is an insulating material, for quite some amount of electric field, you will be able to resist the electric field, external electric field's influence. This is because when you apply an external electric field, for example, you apply positive bias on the top electrode and negative on the bottom electrode, the anion part will be slightly displaced towards the top electrode because that is negatively charged, so it will move slightly towards the positive electrode, and the cation will displace slightly away from the bottom electrode. At zero bias, the centroids of cation and anion will be very close to each other, but as you start cranking up the electric field, the cation will move closer to the negatively charged bottom electrode and the anion will move slightly towards the top electrode. Okay. Now, if you further increase the applied bias and the electric field becomes comparable to the bond strength of the material, what will happen? The anions will be suddenly ripped out from the molecule and they will start moving towards the top electrode. Okay, and this is called the soft dielectric breakdown of the material. There is a soft dielectric breakdown. What was earlier a dielectric property has broken down because you see a sudden shoot up of current. Now, if you allow this particular process to continue, it may result in a hard dielectric breakdown, which is a permanent change. Remember, in our RAMs, we do not want a permanent change like fuses. We would like a controllable filament which can be obtained through a soft dielectric breakdown. Therefore, it is absolutely essential that when you notice that the soft dielectric breakdown may eventually turn into hard dielectric breakdown, it is important to stop the voltage or the applied voltage from an external circuitry. And this is done by imposing something called the compliance current. So what the compliance current does is, the moment it hits a value of current, it stops the measurement, or it stops the applied bias only to the V forming voltage, or the voltage where you get the particular compliance current. And as a result, during the forming stage, when you apply a forming voltage with a compliance current, as you can see from the schematic, oxygen ions or oxygen anions gain enough energy that they are ripped out of their molecular structure and start moving towards the positively biased top electrode. Okay, and finally, the state that we see after the forming step has been done is, these oxygen ions leave back these oxygen vacancies or substoichiometric oxide, whereas the oxygen ions go and deposit themselves on the top electrode. And this is the configuration which creates a substoichiometric oxide based filament which is conductive. So a natural question that may come to our mind is, why is this substoichiometric oxide behaving in a conductive manner? The first thing to understand is that the substoichiometry is only created in the region where these vacancies occur. So coming back to our original question, why is this substoichiometric oxide conductive? This can be understood by looking at the band diagram. So the band diagram for a pristine oxide is something where you see a very large gap between your conduction band and your valence band. This large gap or band gap is what makes a pristine oxide an insulator. This is because carriers cannot transit from the valence band to the conduction band. However, the moment there is any substoichiometry or defects which are created when these anions are ripped out, you can understand that within the band gap of this defective oxide or substoichiometric oxide, there are defect states which are indicated by these dashed lines. Now, generally in oxides, when there is a oxygen substoichiometry, when oxygen becomes less, it so turns out that these defect states are created near the conduction band. And now these new states near the conduction band can donate electrons to the conduction band, and therefore this new defective system becomes like a conductive element, this localized conductive element which behaves like a filament after the forming step. Okay, now that we understand how the filament is formed, we will next try to understand how does the filament dissolve. Now try to recall, we also saw not only there is a subdivision between the nature of the filament in the form of VCRAM and CBRAM, but also depending on how the filaments are annihilated, there is a further subdivision into electrochemical VCRAM and thermochemical VCRAM. So first, let's look at the electrochemical VCRAM. In the electrochemical VCRAM, you apply a reset voltage which is opposite to that of the set voltage. What does that mean? Remember, for forming this particular filament, you applied a positive bias at the top electrode, whereas the bottom electrode was grounded. Therefore, in the case of electrochemical VCRAM, what you essentially do is, now you apply minus V reset or a negative bias at the top electrode while you keep the bottom electrode grounded. So what happens? imagine if you apply a negative bias at the top electrode, all the negatively charged oxygen anions will now start moving away from this electrode. Not only they will start moving away from the electrode, they will go and reoccupy or refill the vacancies which were once created during the set cycle or during the forming step. And as a result, some part of these oxygen vacancies which were created during forming or set get repaired, and therefore there are no longer any presence of these substoichiometric oxide, and this is termed as the filament getting repaired, or sometimes you also say the filament has got annihilated. Now remember, it is not true that the entire filament always gets annihilated. There is some bit of variation on which part of the filament will get annihilated, and later on we will see that will cause a lot of variability. But be that as it may, so as we saw, these oxygen anions go and fill up these vacancy sites and it repairs the filament, and therefore your device goes back to your high resistance state. Why it goes back to the high resistance state? Simply because there is no direct connection of conductive element between the top and the bottom electrode. How do you set it back? Remember, this is a memory device, so you have to set and reset. The way to set it back is you again apply a positive bias. When the positive bias hits a particular critical threshold, again from this region itself, the same process of ripping out oxygen anions will start. Why will it happen from this region? Because the electric field in this region is maximum. See, because the distance is minimum between the top electrode and this region. When you apply an electric field from the external place, there will be a regrowth of the filament starting from this end only. Why? Because the conductive element or the conductive tip of the filament is closest to the top electrode. And that is why we call electrochemical VC-RAMs as also bipolar devices. What is the meaning of bipolar device? It means that the polarity required for reset is opposite to the polarity which is required for set. Okay, common oxides which show bipolar electrochemical VC-RAM behavior is HFO2 and TiO2. Okay, so let us see some practical examples of valence change RAMs which behave in an electrochemical manner. So as we discussed in the previous slide, an electrochemical VC-RAM cell moves from the high resistance state to low resistance state back and forth through the movement of this oxygen anions or oxygen ions. And what is very remarkable is that these conductive filaments can actually be seen, literally seen, under a transmission electron microscope. So this is a transmission electron microscope of a cross-section of a platinum, hafnia and platinum device. And as you can see, during the set cycle, what happens is there is some oxygen deficient areas which constitute the filament. Okay, with this physical understanding, let us now see what is the impact in IV characteristics. So this is the prototypical IV characteristics of a electrochemical VC-RAM device, and this is an actually measured device which constitutes of a tantalum oxide RRAM sandwiched between two inert electrodes. The first thing that we notice in these devices, as we had discussed in the previous slide, is that these devices are inherently bipolar. The meaning of bipolar is that the set cycle is happening in the positive polarity, whereas to reset the cycle you need opposite polarity. And this is common sense because the set process pulls the oxygen anions away from the created defects, whereas the reset pushes them back into the vacancy and these defects. Okay, the other thing that we see is that the forming voltage is much greater than the set voltage. So as you can see in this graph, this is your forming voltage. During forming voltage, you turn a as fabricated device or a virgin device to a conductive element. So this is the first formation of your conductive filament. and this happens at roughly 3 volts. But subsequent set cycles require much lower voltage of only 0.5 volts. This you can understand by looking back at your previous slide. Remember, once a filament is formed, the annihilation is only partial. So therefore, now to recreate the filament, you have to only apply a small bias because the net distance between the top electrode and the actual conductive element has shrunk quite drastically. And that is what we generally see, that the forming voltage is generally much greater than the set voltage. And this is an advantage because the forming step is only done once during the life cycle of the device. The other thing that we see is that although the set process is abrupt, the reset process is gradual, and this will become more evident in another example of your SiO2 RRAM device. As you see that your set cycle is absolutely abrupt, your reset cycle is very gradually changing. Why is this the case? This is because during set, once a filament is formed, there is a sudden increase in current, and as we had seen that you have to limit this increase of current by applying a compliance current. By ensuring a compliance current, you can control the size or the number of filaments. So in a simplistic picture here, we had shown that there is only one filament, but throughout the area of the top and bottom electrode cross section, there can be one or multiple filaments. So what the compliance current essentially does, apart from ensuring there is no hard dielectric breakdown, it also controls the size and number of filaments. As you can anticipate, higher the compliance current, higher the compliance current, you are changing the compliance current by an order of magnitude from 10 microamps to almost 10 milliamps, larger will be the number or size of the element, and therefore lower will be the resistance of the collective filaments, and therefore larger will be the current of the device. Okay, this is about compliance current. Next, we see that the reset cycle is gradual because the process of filling back the vacancies happens one by one, and this happens over different voltages or over different electric fields. So partially filled vacancies will give you slightly higher resistance compared to completely filled vacancies, which will give you very high resistance. Finally, the last thing that we see is that the reset currents and reset voltages are quite similar to the set currents and set voltages. And this is quite understandable because the set and reset cycle in an electrochemical VCRAM are just opposites or complementary to each other. They are the same process but happening in two opposite ends of polarity. In one, the oxygen ions are getting ripped out, creating vacancies. In the other, which is the reset, the oxygen vacancies are getting filled with ions. With this understanding, let's move on to the second subdivision in VCRAMs based on the dissolution of conductive filaments. The second mechanism, as we had studied, was your thermochemical reset. So the thermochemical way of dissolution of the created filament happens through Joule heating. So in this kind of mechanism, since Joule heating is polarity agnostic, you can apply any polarity of V reset. Whether you apply positive or negative V reset, it makes no difference, and that is what I have indicated through this modulus sign. So when you apply a positive or negative V reset for a thermochemical cell, very high reset current flows, which causes a lot of Joule heating. What does this Joule heating do? The Joule heating catalyzes the oxygen migration not only from top electrode but also from neighboring oxides to donate some of the oxygen molecules to fill up these vacancies. And because of this very localized Joule heating, there is a repair in the filament. This repair of filament happens because of the diffusion of oxygen anions from neighboring regions which come and fill the vacancies, therefore repair the filament and puts the device back into HRS. All of this is catalyzed by localized Joule heating. And therefore we say that thermochemical devices are inherently polarity agnostic. And therefore thermochemically driven VCRAM cells are called unipolar devices. Some examples of unipolar thermochemical VCRAMs are NiO nickel oxide and aluminum oxide based RRAM cells. So let us look at some practical examples of thermochemically based VCRAM cells. As you can see in this image, thermochemical transition from set to reset happens primarily because of dissolution of the filament due to Joule heating, and that also has been shown through transmission electron microscopy. So this is the creation of a filament, and this is the dissolution when huge amount of current was passed through this conductive filament. Next, let us look at the IV characteristics of your VCRAM cells. And as you see in your IV characteristics, that these devices are inherently unipolar. What does it mean? This means while the set is happening at the positive polarity, even reset can happen at the same polarity. However, notice, in order to limit the growth of the filament while you had applied a compliance current in the set cycle, it is absolutely essential to remove this compliance current when you are facilitating the reset cycle. If you restrict the compliance current even in reset cycle, there will not be enough I reset to induce this Joule heating. That is the first thing. The second thing that we notice is that the set process and the reset process in case of a thermochemically driven VCRAM is abrupt. This happens because the reset now is not driven by electric fields. There is no filling of vacancies. This happens at a critical amount of localized Joule heating, which has nothing to do with electric field. Only high reset current suddenly makes this transition, and therefore generally the reset of thermochemical VCRAMs is also very abrupt. Also similar to what we saw in the electrochemical cell, the compliance current can influence the size and number of filaments, therefore deciding the resistance in the LRS state. However, the biggest difference we see in thermochemical cells when we compare it with electrochemical cells is the operating conditions both for voltage and for current of set versus reset. As we can see that the reset happens at much smaller bias compared to the set bias. So V reset is much smaller than V set. However, the reset current is much greater than the set current. But a very important thing to understand, especially if you are going to fabricate and measure these devices just like we do in our research group, it is very important to know that you have to release the compliance current during a reset cycle for allowing the Joule heating to happen. Okay, with this understanding, let's go to the second subclass of RRAMs that we had discussed, which is your conductive bridge random access memories. So in conductive bridge random access memories, try to recall, while the bottom electrode was a completely inert material, the filament formation was happening due to the top electrode, which was your active element. Why was the top electrode called active metal? Because it constituted of low work function, high diffusivity metals such as copper and silver. In between, you had a solid electrolyte which allowed the filament formation through the diffusion of these copper and silver cations. Therefore, in valence changer RRAMs, while the filament was happening due to the movement of oxygen anions or some anion, in conductive bridge RAM, we will see that the filament formation is happening due to the movement of cations. So how does that happen? let's see in the next slide. So let us consider first the pristine state of a conductive bridge RAM. And as we can see, in the off state or the pristine state, you had a copper top electrode, you had a solid electrolyte, and you had a platinum based bottom electrode which is inert. Now, when you start applying positive bias to this top electrode, two special things happen. The first thing is that, so this positive bias on the top electrode easily ionizes copper and silver. Why? Because you had chosen them as low work function metals. So they ionize copper by pulling out electrons through this positive bias. Not only that, as you can see in the second figure, these ionized copper cations, by the virtue that they are easily diffusible through this solid electrolyte, start drifting towards the platinum electrode, because the platinum electrode has at a negative potential. So these copper ions which have got ionized because of the presence of this positive terminal now start getting repelled from this positive terminal and start moving towards this negative terminal. In the third step, what happens is the copper ions which go and meet this platinum electrode which is negatively biased take an electron from this platinum material. So basically what happens is this cation gets neutralized by accepting an electron from the platinum metal and becomes again a copper atom. Now it cannot move any further, therefore it starts getting deposited at the platinum electrode. And gradually what happens is a filament starts building. As you keep increasing the bias, more such copper atoms start getting ionized from your copper electrode and go and travel to the filament and get reduced, therefore becoming copper metal. This process stops when there is a complete filament which forms as is shown in the fourth image. When this filament is completed, current suddenly jumps up, as you can see in this IV characteristic, and you have to control the formation of this filament again by applying a compliance current. Okay, so this is the formation of the filament through first ionization of the copper or silver atom into cation and the diffusion of the cation to the inert electrode. Next, we will see how the filament gets dissolved. The filament gets dissolved by exactly the opposite process. Now, by switching the polarity, making sure that your active material has negative and your inert material has positive polarity, the exact opposite process starts happening, which is the copper loses an electron, becomes Cu plus and drifts towards the negative terminal, thereby dissolving the filament. So when you apply positive at Cu, the filament gets formed. When you apply minus at the active material or copper, the filament gets dissolved. And therefore, this is an inherently electrochemical process, because just like in electrochemical VC-RAM, the anions, oxygen anions, were being ripped out of or pushed back into the vacancies through opposite polarity of electric field. Same thing is happening in conductive bridge RAM, but the filament constitutes of copper cations or silver cations. So let us look at some practical examples of CB-RAM. So as you can see, the filaments in CB-RAM can also be imaged through transmission electron microscopy. This is your platinum electrode, which is a high work function inert material, and this is your silver, which is your active material. This is your oxide or your solid electrolyte, and this is the formation of your conductive filament consisting of silver atoms. Also, let's look at the IV characteristics of a CB-RAM device, and the first thing we notice, both in copper based and silver based CB-RAMs is they are inherently bipolar in nature. Bipolar because the process is electrochemically driven. It depends on the polarity of electric field. Also, what we see is that both the set and reset for CB-RAMs is absolutely abrupt. This is very easy to understand because the filament is constituted of these copper or silver physical filament. When this filament is formed, the current suddenly shoots up, and at a critical voltage, when the filament is broken, the current suddenly shoots down as well. That is why set and reset is inherently abrupt. Also, we find that similar to VC-RAMs, the compliance current is what controls the size and the number of filaments, as is very clear by changing the compliance current of this particular device shown in this graph. Finally, we note that both the reset currents and reset voltages are similar to the set current and set voltages in the case of CB-RAM electrochemical cell, simply because they are complementary processes. Okay, with this we will conclude our current lecture. In our current lecture, we saw electrochemical and thermochemical operation of VC-RAM, and also we saw the electrochemical operation of CB-RAM. With this, we conclude the fundamental aspects of RRAM devices, and in the next class we will look at some RRAM performance metrics, and we will also discuss the commercialization efforts which are put in RRAM devices. Thank you very much for your attention. See you in the next class.